What specific problem does DAEDAL aim to solve regarding the limitations of traditional diffusion large language models, DLLMs?
DAEDAL aims to solve the fundamental limitation of traditional diffusion large language models, DLLMs, related to their static predefined output length during inference. This rigidity leads to a dilemma where an insufficiently short length can hinder the model's ability to address complex tasks, while an excessively long length incurs computational overhead and may degrade performance. DAEDAL introduces a dynamic adaptive length expansion strategy that allows the model to start with a short initial length and iteratively adjust it based on the model's confidence in generating end-of-sequence EOS tokens. This approach not only enables the model to allocate an appropriate sequence length for each task, but also enhances its ability to insert additional space for reasoning where needed, thereby improving both performance and computational efficiency. Ultimately, DAEDAL addresses the need for flexible output length adaptation, which is a critical gap in the existing DLLM inference strategies.
How does the proposed DAEDAL method work? Illustrate the process step by step, particularly focusing on both stages, initial length adjustment and iterative mask insertion.
The proposed DAEDAL method operates in two distinct stages: initial length adjustment and iterative mask insertion. 1. Initial length adjustment. This stage begins with a short initial generation length. The model evaluates its confidence in predicting an end-of-sequence EOS token at the sequence's end. If the confidence is below a predefined threshold, indicating that the current length is insufficient, DAEDAL appends additional masked tokens to the sequence. This process iterates until the EOS confidence surpasses the threshold or a maximum length is reached, allowing the model to dynamically allocate a task-appropriate length before the denoising process starts. 2. Iterative mask insertion. During the denoising process, this stage enhances generation flexibility by identifying masked positions with low prediction confidence. Instead of simply remasking these tokens, DAEDAL marks them as expansion points and replaces a single mask token with multiple mask tokens, effectively inserting additional space into the sequence. This allows the model to refine its reasoning and articulate complex thoughts more effectively, adapting in real time to the needs of the task. Together, these stages enable DAEDAL to overcome the limitations of static length constraints in DLLMs, improving both performance and computational efficiency.
Can you provide a simple yet illustrative example demonstrating how DAEDAL dynamically adjusts the sequence length during the denoising process?
DAEDAL dynamically adjusts the sequence length during the denoising process through its two-stage mechanism. For instance, in the initial length adjustment phase, if the model starts with a short initial length and predicts an end-of-sequence EOS token with low confidence, it interprets this as a signal that the current length is insufficient. Consequently, the model appends additional mask tokens to the end of the sequence, effectively expanding the length until the EOS confidence surpasses a predefined threshold. In the subsequent iterative mask insertion phase, if the model encounters a masked position with low prediction confidence during denoising, it marks this position as an expansion point and replaces the single mask token with multiple mask tokens, thereby inserting more space for complex reasoning. This adaptive approach allows DAEDAL to refine its output dynamically, ensuring that the model can articulate its responses effectively based on the task's requirements.
What are the theoretical and practical benefits of DAEDAL compared to fixed-length denoising strategies in terms of performance and computational efficiency?
DAEDAL offers significant theoretical and practical benefits over fixed-length denoising strategies by enabling dynamic length adaptation, which enhances both performance and computational efficiency. Theoretically, DAEDAL leverages the model's confidence in predicting end-of-sequence EOS tokens to determine the sufficiency of the current sequence length, allowing it to adjust dynamically based on task requirements. Practically, this results in a more efficient allocation of computational resources, as DAEDAL can start with a short initial length and expand only as needed, avoiding the computational overhead associated with unnecessarily long sequences. Experimental results demonstrate that DAEDAL achieves performance comparable to, and sometimes superior to, meticulously tuned fixed-length baselines while generating fewer total tokens, leading to a higher effective token ratio. This adaptability not only improves model performance, but also minimizes wasted resources on generating padding tokens, thereby enhancing overall computational efficiency.
Describe the experimental validation process for DAEDAL. What benchmarks were used, and what metrics were employed to assess its effectiveness?
The experimental validation process for DAEDAL involved comprehensive evaluations across 4 benchmarks: GSM 8K for grade school math word problems, Math 500 for competition-level mathematics, MBPP for entry-level Python tasks, and Human Eval for program synthesis capabilities. Performance on GSM 8K and Math 500 was measured by accuracy, while for code generation tasks, the pass-at-1 metric was used to assess the correctness of the generated code in a single attempt. The experiments compared DAEDAL against fixed-length denoising baselines, which required manual tuning of generation lengths across 6 configurations ranging from 64 to 2048 tokens. Key metrics included the total number of tokens generated, the number of effective tokens used to answer the question, and the effective token ratio, which reflects the efficiency of token usage. The results demonstrated that DAEDAL not only achieved strong performance, but also significantly improved computational efficiency compared to the fixed-length baselines.
What limitations or drawbacks have been identified for DAEDAL, and how do they impact its applicability in real-world scenarios?
The primary limitation identified for DAEDAL is its reliance on the initial length setting, which, while it can start from a short unified length, still requires a reasonable estimate to ensure effective global planning. If the initial length is too constrained, the model's ability to form a coherent response is compromised, potentially limiting performance despite subsequent local expansions. Additionally, the performance of the iterative mask insertion stage is sensitive to the initial length. Starting from a very short length may hinder its effectiveness compared to a more appropriate length. Furthermore, while DAEDAL demonstrates robustness to various hyperparameters, including the expansion factor and EOS confidence window size, its performance can still degrade if the initial length is not adequately set. These limitations suggest that in real-world applications, careful consideration of the initial length is necessary to maximize DAEDAL's effectiveness, which may complicate its deployment in diverse scenarios where task requirements vary significantly.